Hi, we're Team Trash Trolls. Our product is designed to remove methane from landfills before it enters the environment. Our goal is to fight climate change and get on the solution side of the problem. With widespread use of our product, we hope to empower people to think globally and act locally.
Climate change is one of the most pressing issues of our time. Global temperatures are rising as a result of increasing concentrations of greenhouse gases. Humans are major contributors to greenhouse emissions. Two important human-generated greenhouse gases are carbon dioxide and methane. According to the EPA, methane represents 10% of yearly greenhouse gas emissions. Methane has a 25 times greater warming factor than carbon dioxide. Landfills represent 24% of all anthropogenic methane emissions in the US and 30% of those in Europe. Many do not have the infrastructure in place to recover methane for energy, and even with gas recovery systems, 10% to 65% of all methane emissions throughout the landfill's lifetime go uncaptured. Climate change is an overwhelming problem, and it can feel hopeless for individuals who want to make a difference. What if there was a way to make a difference and have a meaningful impact? Our product, Trash Trolls, aims to address this issue.
Our product consists of pea-sized spheres that are meant to be scooped into a trash bag before it is taken to the dump. These spheres are made up of a biodegradable plastic and 3 species of naturally occurring microbes. We hope to actively fight climate change in a way that does not involve politics. The landfill consists of 4 stages: the operation phase, the closure phase, the active aftercare phase, and the passive aftercare phase. The operation phase is when our trash tools would make the most impact. This is when the landfill has trash being added to it, often with no covering. In a traditional landfill, gas recovery systems would capture 35% of the methane emissions. To estimate the amount of methane our product captures, we multiplied the portion of our landfill our product covers by our product's methane capture efficiency and the amount of methane remaining after gas recovery systems. Then, we add the methane captured by gas recovery systems to determine the total amount of methane captured. For all of our estimates, we will be assuming 100% coverage in order to emphasize the long-term potential of our product. Using this method, we estimate our product would bring the total amount of methane captured up to 67.5% for this phase, which represents a yearly reduction of 9.5 billion kilograms of methane. The second most important phase for our product is the passive aftercare phase, which is when gas recovery systems are no longer in operation and methane emissions level off at a relatively low magnitude. The addition of our product would be expected to raise methane capture from 0% to 50%, which is a yearly reduction of approximately 2.3 billion kilograms of methane. Overall phases, our product has the potential to reduce yearly methane emissions by 13.6 billion kilograms, which is 26.2% of global landfill methane emissions. We'd like to discuss a potential collaboration with a landfill to test how our product would work alongside a methane capturing system in the future. We've decided to include both aerobic and anaerobic methanotropes in our product to increase the chance of survival in diverse environments. In the aerobic process, a series of oxidation reactions results in the conversion of methane and molecular oxygen into carbon dioxide and water. The other 2 species of microbes are an anaerobic archaea or ANME and a sulfate-reducing bacteria or SRB. These 2 species work together to form anaerobic methane oxidation, which results in the conversion of methane and sulfate to carbon dioxide and bisulfide. All 3 species we're using have been found in studies of landfill microbe diversity, though the exact levels of prevalence are not known. Dormancy in our aerobic methanotrope can be produced using a simple heat treatment. The aerobes will remain dormant until they are re-wetted by water present in landfills. Anaerobic dormancy can be produced simply by depriving the 2 species of methane. Under these conditions, the ANME and SRB are capable of surviving at least 9 months and will recover once in the presence of methane.
The methanotropes in our product will be encapsulated with a polyvinyl alcohol and potato starch membrane. Polyvinyl alcohol, or PVA, is a water-soluble and biodegradable synthetic polymer. It is also processable and stable enough to maintain structural integrity during periods of storage. PVA has gas barrier properties that shields our microbes from methane when dormant, and high resistance to tears when compared to natural biopolymers. Also, the addition of glycerol increases its flexibility. The starch addition to PVA improves the material's overall water solubility and biodegradability. Although we have not had the opportunity to experiment in the lab, a comparison between two studies shows that PVA starch films biodegrade 4 times faster than films only containing PVA. This suggests that the addition of potato starch will increase the biodegradability of our membrane. Alone, potato starch is brittle and not very processable, but together a PVA starch blend increases processability, biodegradability, and water solubility of the membrane. The membrane film is created by pouring a solution of dissolved PVA, potato starch, and glycerol into a mold, which is then left to dry at room temperature or in an oven. After the film is completely dried, it is ready for encapsulating and housing our methanotrophs. The methanotrophs encapsulated by this membrane will be dormant, so they should not be affected by or have any effect on the material as long as it is stored in a dry area. PVA starch's hydrophilic property makes it a great membrane for preserving dormant organisms that will eventually need to be awakened with water. The trash trolls production begins in the lab, where methanotrophic bacteria and archaea are grown and then packaged in PVA potato starch membranes. Our methanotrophs are considered a biosafety level 1. Glycerol and potato starch come from renewable and sustainable resources. However, we acknowledge that ethylene, which is a precursor molecule to PVA, is primarily derived from fossil fuels. Although it is not our preference to use a petroleum-derived product, PVA has specific properties that are necessary for our membrane, and once we can work in the lab, we hope to find a better alternative. After production, trash trolls would be distributed to grocery stores alongside other household supplies that are sold to the public. The true life cycle of trash trolls begins where most products end, in the landfill. Consumers scoop trash trolls into their trash bag, which makes its way to the landfill. As trash trolls are dispersed throughout the landfill, the PVA starch membrane dissolves and biodegrades, exposing our microbes to the environment and awakening them from dormancy. As existing microbes in the landfill break down organic material, they produce methane. As methane rises through the layers of substrate, the methanotrophs will capture and metabolize the methane. As a result, they will grow and divide, increasing in abundance and decreasing the concentration of methane escaping into the atmosphere. As long as the landfill is still producing methane, trash trolls will continue to convert it to carbon dioxide, which enters the carbon cycle. While this is not a perfect solution, we expect it will cause a significant reduction on the warming effect of greenhouse gases.
In the future, we hope to collaborate with biodegradable bag manufacturers in order to increase dispersal and biodegradation. Although the membrane is non-toxic and the methanotrophs are not known to cause illness, we also think this would be a safer delivery system for people with children or pets. As we scale up and work with bag manufacturers, we hope that our product will become more easily accessible. People that cannot buy trash trolls or are put off by the idea of bacteria will still benefit from the effects of reduced methane levels, cleaner air, and eventually, we hope, a more stable climate. We are also interested in the possibility of incorporating photosynthesizing bacteria to reduce levels of CO2. We know that our product is not a complete solution, but we hope that our research will inspire others to explore methane capture as an innovative way to fight climate change.
Kids, can someone take out the trash?
Me. Hey, Bugger, don't forget the trash trolls. I never forget the trash trolls.
Do you ever wonder what happens to your trash troll after it goes to the landfill? After it leaves your house, it gets dumped along with trash from all around the city. This bag will get buried in a matter of weeks, and conditions for the trash troll to wake up will soon be established. In the U.S. alone, 254 million tons of trash are created each year. And what happens to all of that trash? Microbes break down the organic material into greenhouse gases like methane. Methane provides food for the trash troll, who should be waking up soon. Trash trolls help convert methane to carbon dioxide, reducing the effects of greenhouse gases. In large quantities, trash trolls can make a difference.